to be on the exam next Friday. But we'll probably have a day or two on chapter 4. I thought about having a bye one day, but I think we'll sort of hold it back in reserve. You know what I mean by bye? Like we'll have a day off one day because we're sort of getting ahead, and we could probably get part of chapter 4 on this exam, but y'all'd rather not, right? Yeah. My wife said that we're getting a little too far ahead, so says that we need to, I don't know. Because I'm not used to having 5 exams in this class, and usually chapters 1 and 2 are on the first exam. And what do we have on the first exam? Chapters 1 and 2 mostly. Yeah, so 2.5. So.
This makes most sense together. That one have to do with.
Yeah, so we'll just have 2 and 3. I think that'll work well.
It's probably because we're back in our fans.
You are really smart. There's no doubt about that. This is like the best, like this class, not just y'all, but like people in this class are like the best students at Nichols. Because you've been through like all the calculus and stuff, and so like if you didn't get through calculus, then you're not here. And I love you guys. No, I'm just joking. No, I do, but not now. All right. All right. Let's see. Let's look at resistivity. We'll watch this video in a bit. We didn't watch the Make Zine video about resistors, did we? We'll hold that off for just a minute more. Let's look at resistivity. Now we can think of electricity like water in pipes. And, a pipe has certain geometrical dimensions. It has 2 dimensions. What are they? Right, the length and then the cross-sectional area. And so we can describe the resistance of a pipe or also a conductor based on those dimensions, the length and the cross-sectional area. So if I have a pipe that is a different cross-sectional area, how is the resistance going to vary with that? If I increase the area, what's going to happen to the resistance of that pipe? That is, if I make it bigger, is it going to be easier or more difficult? It's going to be easier, which means lower resistance. So that's going to be an inverse proportionality with the resistance. That is, if the area goes up, the resistance goes down. That's an inverse proportionality. Whereas if I have say a short hose or a very long hose, which is harder to push a fluid through? The long one. So with the length, if the length goes up, the resistance does what? It also goes up. Longer pipes are harder to push water through, for example. And the same is true for electricity. So this analogy holds pretty well with electricity. So then we have a direct proportionality with length, so that if L goes up, R goes up. We're also going to use the resistivity, which is going to be an experimentally determined value, and it's just going to be directly proportional to the resistance. So the resistivity is dependent on the material, and it's directly proportional. So which has a higher resistivity, wood or copper, would you say? Wood is an insulator, so it has a much higher resistivity. So this resistivity is just something that's dependent upon the material. And then we can combine these 3 things, and we get an expression for the resistance that is proportional to these 3 quantities, or is equal to these 3 quantities, rho times L over A. This is on your equation sheet. And it's sort of akin to, if you recall with capacitors, we had an equation for the capacitance based on the geometrical quantities, geometrical dimensions. Right, remember it, epsilon A over D. So this is similar to that. Right, and then don't also forget that we also have Ohm's law, which defines what the resistance is based on the voltage and the current. So that's also similar to what we have for the capacitors. Remember we had Q equals CV, which isn't the same as Ohm's law, but at least in this, it's similar in the way that we describe it. All right, so let's try a couple little questions on this. 2 wires A and B are made of the same metal, so they have the same resistivity, and they have the same length. But the resistance of wire A is equal to 4 times the resistance of wire B. How do their diameters compare? You want to remember a couple of things. I always like to do with questions like this is just ask myself, is wire A bigger or smaller than wire B? And once you answer that question, you can get rid of three options here, either A, B, C, or C, D, E. And then ask yourself, how do their diameters compare? And also remember here that I'm not asking for area, I'm asking for the diameter. First ask yourself the question, is wire A bigger or smaller than wire B? And then, how do their diameters compare? All right, guys, you want to rethink what you're writing, because right now only like one of you has the right answer. Okay, maybe two, I'm not sure. But remember, we're talking about diameter, not area. And if you recall, area is proportional to the diameter, what? Squared, right. So rethink this. All right, there we go. All right, just a few more seconds, I'll stop. I'm going to stop at 2:58. Okay, that's a little better. So, first of all, we can show that wire A is smaller than wire B. So this is wire A, and this is wire B. All right, A, B. Because the resistance of A is bigger than B. Oh, they should be the same length, right? So. All right, so wire A is smaller than wire B, so that gets rid of these three options. So it is either D or E, and most of you did D or E. But I also know that the resistance of wire A is 4 times that of wire B. So I know that my resistance is rho L over A. So in order to get a resistance that is 4 times that, if it's only the areas that are different, I need a 1/4 difference in the area between the two, right, to give me 4 times the resistance. So what is going to be the difference in the diameter? I need a 1/4 difference in the area. So what is the difference in the diameter? Y'all go ahead and try that. It's either D or E. We've already determined that. But y'all are split evenly between those two. All right, I'll stop at 30 seconds. Very good. D is the right answer. Because that area is proportional to the diameter squared, if you have half the diameter, you'll have 1/4 of the area. A half squared is 1/4. We'll see some similar strains of questions like that in the concept test later. Let's try this one. If you have an unknown metal, a really nice way to find its the type of metal that it is to measure its resistivity, and that's what we're doing here. It's calculating its resistivity and then picking it from a list of known metals. couple steps here. Use Ohm's law, find the resistance, and then determine the resistivity. About 15 more seconds, 20 seconds or so. I'll stop at 310, 310. All right, D is the correct answer. Very good. It is tungsten. As I said, this is a nice way to determine unknown metals. So you just put a voltage across it, measure the current, and then you can find the resistance, V over I, which is going to be 0.07. Okay, 0.07. Excuse me, 0. Everybody agrees with that? Yeah. And then that's in ohms. And then the resistivity, R is rho L over A. So rho is R A over L. And then if you put in those numbers, you get a resistivity of 5.5 times 10 to the minus 8. Those are in ohm meters, which is, you'd look that up in a table and you'd find, oh, this is tungsten, or whatever. All right? There are other ways to determine unknown metals, but that's a nice easy way. Let's take a minute and we'll watch this little magazine video. It's really just a few minutes long, but it's kind of fun. All right. We've sort of been talking about resistors in terms of pipes, and all the textbooks, they'll talk about this sort of electricity-water analogy, and because it fits pretty well, and even when we get into resistors in series and parallel in the next time, it'll fit as well. So we're going to sort of introduce it here. First of all, if we just think of a simple circuit, I have this source of potential, this battery or power supply or whatever it may be, And then, charges come off of this. We think of them as positive charges. They come off and they travel in this direction, which is the conventional direction for current. And we can think about their energy. At this point, when they just come off the high potential side of the battery, are they going to have a lot or a little bit of energy? They're going to have a lot of energy. So if we think about their energy at this point, they have a lot of energy. And then the energy up in the resistor is going to increase or decrease? It'll decrease because they'll do whatever it is that they're going to do. And usually if it's going through a resistor, it's just going to heat up the resistor and lose a little bit of energy. But it could go into an electric motor or go into a heater, which would turn into heat, or any variety of uses. Whatever you want the electrons to do, they'll do it there. And then when they come back, over here, we're just going to have a little bit of energy. In fact, over here, our energy will be zero before it goes back through the battery again. So we think of our circuit as this cycle. These charges go through our circuit, they gain energy in the battery, and then they lose all of that energy, in fact, as they go through the circuit until they get back to the battery. So we can think about that also. What would be the equivalent if we had a water system like this, where we had water flowing through a pipe, and then we had a paddle wheel here? What would be the equivalent to the battery?
Energy, like pressure.
Right, yeah. So like we have a battery over here that provides energy. What is that going to be in this water system? Huh? No, like in this thing that we have here. The wheel, right? See, yeah, you have this wheel right here, and this would be the equivalent to our battery. So it's what gives the water energy. And then as it comes up here, we have these wires, which are these parts of the pipe, and they have a very low resistance. As you measured in lab, wires actually do have some resistance. It's very, very low. But then when the pipe gets smaller up here, this would be the equivalent of our resistor. And the water would actually lose energy as it tries to go through that little bitty pipe. Now, if you have resistors in parallel, like this, here you would have a small resistor, and it's shown by here, something with a big area. And here I would have a big resistor, something with a very small area. So I have my battery down here pushing the water flowing up through here. Now at this point the water breaks into two pieces. Some of the water goes here, and then some of the water goes here. Which of those branches is going to get the most water flow? The one on the top, the small pipe, or the one on the bottom, the big pipe? Those are Kim White's. You're welcome to have one, but they're very scratchy. Which one will get the most water flow? Right, the big one, right? Because it's easier to push water through. And in a similar way, you're going to get a big current here and a small current here. We'll see that in the next chapter. We'll do resistors in series and parallel until you're sick of them. Okay? Another thing that comes up, like if we imagine I have these two currents, I'll go and introduce this. I have some current here, I, and then I'll call this I1, and I'll call this I2. We're going to have a rule that's going to come up in the next chapter, and that is that I is equal to I1 plus I2. That should make intuitive sense to you, right? Because the same is true for fluids, that if I have water going through a pipe and it splits into two, I'm not going to lose any of that water, right? So the sum of the two flows of water going out of the junction will equal the sum going in. So I could write it also as I in equals I out. This is one of our basic tools for electrical circuits. We'll see it again, but it's called the Junction Rule. All right, you won't see it on this test.
It might seem kind of, maybe I'm thinking too much of it, but if that is like a water system or whatever, normally if that was the way it was, the top would have the pressure coming through. If it was a smaller diameter hose.
Right.
So does that have anything to do with the current? Or is it
no, it wouldn't have smaller pressure. It would have a lower pressure.
So if you had say you had pressure coming through a hose, and you put your finger on the end of it, it's going to create the stream's going to go out farther because the pressure you made it smaller.
Yeah, we didn't do fluids last semester because they took it out of the 201 course. But with fluids, if your velocity this doesn't make intuitive sense. But if your velocity goes up, which is what's going to happen up here, the pressure goes down. All right. So high velocity fluids have a low pressure. Let's give an example. Airplane wings, right? This isn't exactly correct, but I have an airplane wing that looks like this. I have streamlines of air that break over it. And when they break at this point, that if you think of a particle of air that travels along here, that same particles are going to come back at this point. Because otherwise you get a vacuum, right? And you don't want a vacuum. So you have the higher velocity air up here and the lower velocity air down here. So that means that you get a low pressure and a high pressure down here. And that's what gives you lift, right? Because I have a high pressure on the bottom and it goes up. So, does that answer your question? That's sort of a sidetrack, but.
I wasn't sure if there's, since that answers exactly what I was asking. So
Okay.
less current up at the top.
Right, and a lower pressure. Yeah, but the velocity is actually bigger, but a lower pressure. You're right about that. The velocity is bigger. All right. Okay, our last topic here is on electrical energy and power. If you've ever done any electrical work in your house, you've probably used these series of equations. And electricians will use them quite a bit. All right, so batteries convert chemical energy to electrical, which is then converted, as we said before, to whatever you want: thermal energy, mechanical, or, we can convert it to light. Whatever it is that you want your electricity to do, it'll convert it back into some other usable form of energy. So because of that, it's useful just to be able to describe the amount of energy that's provided by a circuit. Now remember what voltage is?
What is that second one?
Mechanical, like something moving. Okay, no, you're getting ahead of me. So what is voltage defined as? Basic. Something over something. Huh? Wait, energy per charge, right? Thank you, Brittany. So voltage is energy per charge. So then we can say the energy then is going to be V times Q, right? Just our basic idea of energy. Electrical energy is our voltage times our charge based on that definition. And does anybody recall what power is in terms of energy from last semester? Energy over time, right? So our power is equal to energy over time. And so I can say then, well, this is energy over time, which equals VQ divided by T. But if you recall, we defined our current I as Q divided by T. So notice we have this Q over T term here. So I can get an expression for power that is what? V times your current. So this is one of our basic guiding principles when we're looking at circuits, is that the power on any certain device is the voltage across that device times the current. Any electrical device, which we'll just be dealing with, resistors. What is the unit of power? What is the unit for power? Yes, that was a statement. That wasn't a question. Watt is the unit for power. I think I used that last semester. Yeah, so the unit for power is the watt. Yeah, it's abbreviated. 1 watt is equivalent to 1 joule per second. And let's see, we can rewrite Ohm's law in a couple of different ways, just by substituting, or we can rewrite this power equation by substituting Ohm's law. So P was VI, So we can say P is also I times R times I. That's just substituting this in for V. I get I squared R. Let's see what I'm doing. I'm just substituting Ohm's law in. What's the other expression then going to be? V times what? Huh? No. V over R, right. So I can just solve this for I, which is going to be V over R, and then I'll get V squared over R. So these are just alternate expressions for the power. I think these are both on your equation sheet. P is VI, P is I squared R, and P is V squared R. V squared over R, rather. We'll see some cases where those are nice to use, but you can always just remember the P equals VI and use Ohm's law and consort with that to figure out whatever it is that you're looking for. All right. Electricians often use this when you're building a house. You have to estimate how much current is going to be drawn onto a particular circuit so that that circuit's not overloaded. And you can take your power ratings from your appliances or whatever it is that you're using and figure out how much total current is drawn on a particular circuit. We'll look at that in the next chapter. It's fairly interesting. You ever seen this? P is VI? No. So like a higher wattage appliance, like your, I don't know, your toaster oven, which is like 1,000 watts, or your hair dryer, which is like 1,000 watts too, is that going to pull a lot of current or not very much current? As compared to a radio, which is like, 20 watts. It pulls a lot of current. Like your hair dryer is basically the highest powered thing in your house, unless you have a electric oven or something. All right, these are just some sample MCAT questions. These are pretty simple. I just wanted to show you all some ideas. I think only one of you is MCAT here, but I just pulled these from Kaplan. So if a current of 1 amp flows through a circuit for 5 seconds, how much charge is flowed? Well, this is just based on our definition for current. All right, so Q is current times time. It's going to be 1 amp times 5 seconds, which is 5 coulombs of charge. Let's try this one as a clicker question. I'll give you 3 options. Yeah. So it tells you that R1 to R2 is 1 to 2. That's the same as writing 1 over 2. So now I want to know, what is the ratio of their resistivities? Is it 2 to 1? Is it 1 to 2? Or is it 1 to 1? What are the ratio of their resistivities? My understanding, the MCAT, they like to ask questions like this, sort of. Ratios, relationships, that kind of thing. Remember, our guiding thing here is R is rho L over A. So how is R related to the resistivity rho? I'll stop at 110, 110. It's 5 more seconds. Okay, B is the correct answer. I have a direct proportionality between R and rho. So whatever ratio you have for R, you'll have the same for rho. So rho is going to have a ratio of 1 over 2. It should be the same as R. What would A1 to A2 be, by the way? Yeah, let's do it as a clicker question. That's a good idea. So, what is A1 to A2 going to be? Now, it's good to have extra clicker questions, because I sort of start out the way I set your level for the clicker questions is I say, well, I'm going to ask 150 questions this semester. But as you know, we often throw in extra questions like this. So it's just extra opportunity for you to pick up points. And you get points even if you get them wrong. So it's a good deal. All right, I'll stop at 45. Very good. So it's an inverse proportionality here. So the ratio is now 2 to 1, not 1 to 2, because of this inverse proportionality. All right, let's wrap up with this last question. This is very interesting. We'll talk about transformers in the next chapter, but a transformer transforms an input voltage and produces an output voltage that is larger or smaller than the input voltage. This happens in those big oil cans that sit outside your house. They take a voltage from the power lines out on the street, and they convert it to a voltage that you can use in your house. Do you think that the voltage in the power lines is bigger or smaller than the voltage in your household? It's bigger. It's like 3,000 or 4,000 volts. And in your house, you have what? We have 110 or 220. We'll call it 120. So in your house, we have 120 volts. It's a little bit different because it's AC voltage, and so, but we're gonna call it 120. But we'll talk about more about that next chapter. So the transformer takes a high voltage and steps it down to a low voltage. So that's called a step-down transformer. Or you can have a transformer, which is like the one here in this question, that is a step-up transformer. So a step-up transformer is going to do what? Where it's going to take a low voltage and increase it to a higher voltage. So, I mean, voltage is energy, right? Energy per charge. So it seems like that transformer is actually either producing or taking away energy, right? Does it seem that way? But it's not, right? The transformer is a passive device. Like, it doesn't actually generate electricity in any way. But the reason that it does this, and it says here, it says that the voltage is changed, but energy is not. So the input power is equal to the output power. That is to say that Pn equals P out. Or Vn, In, equals V out, I out. So in the case of the transformer outside your house, the step-down transformer, it takes a large voltage and makes it a smaller voltage. You think the current in the lines outside your house is bigger or smaller than the current inside your house? It's not the same. Because the power has to remain the same. The energy per time has to remain the same. It's taking the voltage and making it smaller. So what is it doing to the current? You get a much bigger current where? Outside or inside? Inside. Much bigger current inside your house. We'll talk about this next chapter, but it's very interesting how transformers work, and they make this AC electricity very easy for us to use. So in this case, it says that our V out is 300% larger than V in. So V out equals 3 times V in. So I out is going to equal what amount of I in? Is it, we'll do it as a quick question, A, B, or C? Is I out equal to 3 times I in, 1/3 I in, or is it equal to I in? If our V out is 3 times V in, what is our I out? This is our last question. Y'all going to wrap up. Once you click in, you can back up. I'll stop at 30. 30. All right, B is right. It's a 1/3. We'll talk about that more later, okay? Y'all have a good day, good weekend. Don't work too much. Yeah.
You know, last one.
Absolutely, yeah. Give me just a minute.